Okay, let me present my screen. Can you see my screen right now? Are you able to see my screen? Okay, so can anyone tell me what have we learned in the last lecture? Okay, maybe I randomly pick the people. Lu Jui Min, are you here? Mr. or Miss? Miss Lu or Mr. Lu? What have we learned last week? Last lecture, not last week. Whatever came across your mind, just share whatever you know, whatever you can remember. Yeah, Mr. or Miss Lu. Any clue? Or you already completely forgot? Are you here? BCC, FCC. What is this? What is BCC? What is FCC? Can you tell me the full name? Okay. Would you may give me two terms? So maybe I get another person to elaborate more. Okay, let's see who else is here. Okay, Lim Chun Wei, what do you think? What have we learned last lecture? What is a BCC or FCC? Yep, body center cubic. BCC is a body center cubic. Then FVCC is a face-centered cubic. Okay, just a quick recap. Last lecture we learned about the solid. Whatever we learned about solid, always we link to the atom. Inside the atom we get the nucleus, proton and electron, all these things. Then we will try to arrange all the atoms together. So you may be in the simple cubic SC, BCC, or FCC. For this and the cubic, simple cubic, it looks like this. For face center, it looks like this, just a simple thing. So in each of the corner, you are going to have one atom. Atom. Okay, this one is a simple cubic. Then regarding the face center cubic, you are going to have the one atom on the surface. One here, then you got six up because got six surface one. Then you also got one body center cubic. So when you have a body center cubic, it just looks like a simple cubic with the atom inside. So can anyone tell me how many atoms in the simple cubic? Last class we worked about that. You should remember that. Yep, Wong Shui say one, which is the correct answer. In the simple cubic, we are going to have one atom. Okay, what about the body-centered cubic? So let me pick another guy. Chia Chai Siu. Are you here? Mr. or Miss Chia? Okay, body-centered. Wait, simple cubic, one. Body-centered cubic, two. Another one. Let's pick another guy. Okay, Chua Yu Yang, are you here? What is the number of the atom in the face center cubic? Face center cubic, yep, 4. Very clever. Everyone can answer me well. 4 atoms. So, in this all the base body center cubic, face center cubic, then we also know how to calculate the surface density and the volume density. Okay, so basically this is all the things that we have learned so far last week. But not last but not least, I will also learn about all the, let's say, structure of the solid. Some is looking like this, then some we arrange randomly, or some maybe have a different region. Then the arrangement is different. Okay, so throughout all the lecture in the microelectronic, we just focus on this only. Okay, and a few of the famous semiconductor that we use is silicon, germanium, and also the gallium arsenide. Okay, so whenever when we talk about the semiconductor, the one thing that we know is always the transistor. Okay, whatever you know in the, let's say, a basic electronic or the analog electronic, we know about the resistor, that may be the diode, or maybe also the, let's say, transistor. All these are semiconductor, or even the capacitor also considered as one. Then, when the time is growing, we can know that Moore's law saying that the number of the transistors on the chip double every 2 years. And the trend has continued for more than half a century and is not expected to stop for another decade. Okay, in our daily life, we always use the transistor. Maybe you know or maybe you don't know. Okay, the transistor is appearing in your handphone, somehow in your handphone, or maybe in your laptop, or even the i3, i5, i7 processor, or maybe already 911. I don't know. Or maybe even your motherboard. Some of you using, let's say, GTS 1080, some of you using the RTS 3080, something like that. All these consist of the transistor. But according to the Moore's law, the transistor is growing larger and larger. But what is the number of the growing? So here's a really good video. It can demonstrate the growing of the transistor according to the Moore's law. Let's see this. Okay, let me start present first. Okay, sorry, wait a moment. Let me share my screen again. Tab. Okay, let's replay. Can you see the screen right now? Are you able to see the YouTube video?
Yes.
Okay, let me try to play it. Okay, what do you think, everyone? So after seeing the video, so I believe some of you may have seen this video before. So for information, some of the company, for example, like the TSMC in the Taiwan, they already start developing the even smaller chip that can contain more and more transistor. So somehow you can see that in the video actually, some of the product developed by, for example, NVIDIA or the Intel already somehow exceed the prediction of the Moore's law. Okay, we can see that the technology are getting growing stronger and stronger. And one of the big company is the TSMC. Okay, I think some of you may know. He is the one who created the wafer. Then I think Intel also somehow want to compete with TSMC right now. As we know, the TSMC also come from the Taiwan. So maybe somehow US market also want to fight together. Okay. So whenever when we talk about all the Moore's law, all the things, all the small things, all the chip, we need to do the fabrication. Okay. What is the fabrication about? So last time we tend to see the transistor in this normal way. For example, this is the transistor. Okay. We tend to see this everywhere. Okay. But have you ever imagined that some of the i3 processor, okay, for example, a processor like this, maybe just a tiny processor on your finger, something like that only, and it contains a lot of the transistor inside. Unlike the one that we see normally, just now when you see normally it's kind of big, right? Yes, you got a big one, big back box. Then here are three gate. We got a drain, source, and the gate, everything. Okay, but actually transistor can be much smaller according to what we have used in our work. Let's say computer or even the handphone processor. Some of you may be using the Huawei, they are using a Kirin processor, something like that. Some of you may be using the, let's say laptop, you're using the i7 processor, i7 maybe 11th generation. Okay, so inside they got a lot of transistor. Then the transistor is very small until we cannot see using the naked eye. We might be using the microscope to see all the tiny transistor. Okay, so in order for us to put a transistor all together, we need to put on the wafer. The wafer is not like the wafer that we eat. Okay, it's something like this wafer. For this wafer, okay, electronic. Okay, this is the wafer, not the wafer that we eat. You see, this one is consists of germanium. This one is made of the germanium. Okay, you can see here there are a lot of small rectangular boxes. Can you see the wafer? I believe you can see, right? Or the wafer here. Inside there, you can see actually a lot of small square box. But inside this small square box, actually it contains some of the transistor inside. So that's why you can see that wafer maybe just, you can see what's the size of the wafer. Okay, so you can see 12-inch, 300 mm, which is the 30 cm. We got a smaller one, even the 4-inch. Okay, we got a lot of different wafer size. From the 1975, it's getting this size, then getting bigger, but you can put more and more inside. Okay, this is the benefit of using the wafer. So unlike the PCB lab that we have done maybe during your second year, during your engineering class, we no longer need to use all the transistor with the 3 leg. Okay, we need to know how to design the transistor. So this one no longer used. Right now, everything go to the wafer. Inside the wafer, here's a small square box. Maybe here got a lot of the transistor inside. A lot transistor. Okay. But in order for us to put all the transistor on here, we need to use the process we call it as a fabrication. Okay. So today I'm going to talk about the fabrication. But fabrication actually is basically is a theoretical process. Okay. So you just listen. I think it's somehow a little bit boring for me also. So you just listen how can it be performed. So let's see what's a fabrication. So integrated circuit are created by fabricating all the components and the connection onto the circuit. Then all the integrated circuit process start with a thin slice of silicon known as a wafer. So just now the one that I show you, this wafer. Okay, we also name it as a substrate. Okay, substrate. This one I think is somehow this one is a typo. I will correct later. So each wafer is cut from a single crystal of the element silicon and polished to its final thickness with the atomic smoothness. For example, he wants to make this wafer into a very thin. Okay, let's see what's the thickness. Yes. Okay, I think maybe cannot see the thickness, but actually it's a very tiny thickness. Okay. Okay, never mind. We proceed to our lecture first. So most of the circuit designs, for example, like your i3 or iPhone processor, it fit into a few square centimeters of the silicon area. Then each self-contained area is known as a die. So imagine in this wafer, we split into many small square box. Okay, like we showed you just now. Then inside here, we call one piece as a die. Then inside the die, it contains a lot of integrated circuit. Okay, the detail of the integrated circuit you are going to study in the next semester, year 4, sem 2. Okay, if you want to take it, then you just choose it. Okay, it's one of the elective that you have to choose that. Okay, so after the fabrication, the wafer is cut to produce the independent rectangular dies, often known as the chips, which will be packed to produce the final component you buy at the store. Which means that originally it looked like a piece of this. Okay, then somehow you put into the microchip. Okay, inside there, the die actually is stored inside this black box. Okay, outside is a black box. Then everywhere is a leg for the connection. You can see that actually the small box is actually very small. You even need to use maybe a cutter to move it. You see, it just like maybe let's see who have to do them, I don't know. But some of them already able to design until the nano level. TSMC smaller size. Okay, this one in here is a 14 nano. So let's see what's the smaller size right now. 5 nano process. Okay. Imagine a die, a very small die that can only 5 nanometer multiply 5 nanometer. Then inside there you can put a lot of transistor there. Is that amazing? So this is the technology right now. Okay, but in order for us to create the 5 nano one, we need to do the fabrication. But what's the fabrication about? So this is the chip, the normal chip. So inside there, it contains something like this. This is actually a transistor, okay? But how does it actually look like? So originally, this is the wafer. Okay, let me draw it. This is a wafer. Wafer die, not wafer. Just one of the square box here. Okay, imagine that in this wafer, you want to create one PMOS and one NMOS transistor. Actually, you can split it. Okay, you can split it. You can see something like this. This is a PMOS, this is the NMOS. So in this PMOS and NMOS, you are going to go through some process. For example, you are injecting some specific area here, here and here. Then you are going to put the gate, which is the LED, okay, connection. So if you remember in the transistor, we got three, right? GSD, okay? Then we got a gate, we got a source, we got a drain, right? So actually this is a gate and source, and this is the base. So how are we going to install this 4 leg inside this tiny wafer? So this one is go to the fabrication process. So for your information, actually this one is the NMOS and this one is the PMOS, okay? So you might be asking, why are we going to put these two things together? Okay, originally you can see that this is a P substrate. Okay, if P substrate, we can use it to generate a NMOS transistor here. But let's say if you want to generate the PMOS transistor on the P substrate, what are we going to do? Yes, we can do that by adding the M well here. So P substrate is going to generate the NMOS, but if we need to generate the PMOS, we must use the N substrate. Okay, N substrate, which means the N wafer. Just for example, what is the P substrate and the N substrate different? So let me show here. P substrate is the silicon wafer with majority hole, or you can say as a proton. N substrate, silicon wafer with majority electron. Okay. So normally the P substrate is going to create the NMOS transistor. N substrate is going to create the PMOS transistor. Okay. So far any question first before I proceed? Any question before I proceed? Any question this part first? So if no question, you type a no there. If you have a question, you may ask. Look at this first, the explanation here first. Okay, what about the rest? Okay, so I proceed. So, if you still remember, we got an NMOS transistor and the PMOS transistor, right? Transistor and PMOS transistor. Okay. NMOS is come from the P substrate. PMOS come from the N substrate. Okay. And then, so let's say in this example, this is originally a PMOS P substrate and is used to create the NMOS transistor. Okay, but somehow there are still some extra region here. If we want to create the PMOS transistor on the P substrate, what are we going to do? So we are going to inject some N substrate in this area. The N substrate we call it as a N well. You might be wondering why are we calling this part as the NMOS transistor? Because you can see, if you still remember last time when we were learning about the transistor, we learned about the NPN and PNP, right? Okay, you can refer back to the, let's say, NPN transistor. Not sure if you still remember this or not. Okay, this is a very basic thing. NPN resistor, it flow from here to here, then this one flow from here to here, something like this. Okay, so let's see back to the slide. Okay, this is actually a NMOS, N, P, and N. PMOS, P, N, and P. So that's how we define it, NPN and PNP. Okay, but this is a biological generator, I think some of you may know that. The important thing is how are we going to create this NMOS and the PMOS transistor in the P substrate. Okay, let's continue. What are we going to do it? So originally, this is the wafer. This is a wafer. Okay. So if you want to install the NMOS and the PMOS, NMOS based on the P substrate already fulfilled, but PMOS is based on the N substrate. No N substrate here, so that's why we need to install an N well. Okay, N well is the region that produces the electron to it. Okay, but how are we going to install this N well? At first, we need to put a silicon oxide on the surface. Okay, so you can use the H2O or the O2 in the oxidation furnace. But what is the purpose of putting this? So let's see. So after putting this, we need to put another layer. We call it as a photoresist layer. Be on the SiO2 layer, silicon oxide layer. Why are we going to do this? Okay, just now when I was saying that we want to install the M well here, we want to install somewhere around here. But at this moment, we just want to cut down this area. We want to disturb the area. The remaining one, we don't want to disturb it. So how are we going to install this M well area? We must take a hole. We take a hole, open the area, open the region for it to inject the M well inside. How is the process? We need to use the photoresist to help us. Let's see how. Okay, so what is a photoresist? Photoresist is a light-sensitive organic polymer, so it will change when we expose to the light. Which means that I want to put a layer and we want to expose the UV light here. We inject UV here. So once I inject my UV here, I will somehow remove this area. Okay? So if I successfully remove this area, it will look something like this. Okay? I'm trying to inject the UV light because right now I'm trying to inject the M well in this region. So I will capture this region, but somehow I want to put the UV light to remove all this. Okay, so here's the opening right now. Opening. This one is open. Okay, after this part is open, I further remove this part. I remove this part. I want to remove this part gone. So in this part, I want to use some chemical. Sorry, to remove this. Okay, this is the process. Okay, at first I put the silicon oxide, then I put the photoresist, then I just want to capture this area, so I expose this part to the UV light, so this thing will be open. After that, I put some chemical, remove the SiO2 region. Any questions so far? Is there any question? If no question, then I know. The rest of you? Okay, good. Mostly can understand. Okay, so just now when I mentioned that I'm going to remove this region with the chemical, this part. Then the process of removing it using the chemical, we call it as a etching. So I believe during your, let's say your engineering drawing and CAD, last time when we were dealing with the PCB lab, right? But if some of you may have went through it. So we put the copper board. You remember, we put a copper board into a UV chamber in the, let's say 301. Okay, put it into the copper chamber. UV chamber. I'm not sure if you still remember it. We put a transparent paper on top, right? Then here's a circuit, something like that. You still remember this? We put the transparent paper, then put it here, then UV light go through here. So all the region with the cover will be gone. Then we just remaining all the region in the black cover. Then we put the process into the etching. Okay, I believe some of you may know that you didn't take a diploma or mini project. So same thing happened to this etching. This microelectronic, we are using the same concept. Okay, just that right now I'm using UV light to expose this region, then using the etching to remove the part here. Same concept. Okay. So right now, since this part is open, I'm going to insert the end well pattern. Why are we calling it as a well? Well, I think you all know what's a well, the meaning of the well. Okay, we are going to take the water from the well. Okay, so this one is an end well. We are going to provide the electron from the well. That's why we call it as an end well. Okay, so end well pattern is transferred from the mask to the silicon dioxide surface, creating an opening to the silicon surface, something like this. Okay, so we also somehow remove the photoresist here because no longer need to use one. Okay, so in this process, we are going to insert the end well inside here because we are going to create the PMOS transistor here. So end well is formed with the diffusion or ion plantation. So here is the two process you can put the end well. One is to diffuse it. So whenever we talk about the diffusion is always from the electron of a high concentration to the low concentration. So there are two ways. One is through the diffusion. So I'm trying to put this thing inside the arsenic-rich gas so that it can put all the end well region here. It's from the outside high concentration to the inside low concentration. So it can help to generate this end well. Or we can put the ion binning. We are trying to brush some ion beam here. Okay, the ion beam is based on arsenide. Okay, arsenide ion. Why are we going to use the arsenide? If you still remember in the very first slide, we saying that gallium arsenide is one of the famous semiconductor, which is a compound semiconductor. Okay, so after this, we successfully inject the end well inside here. Okay, so there are two ways. Is using the diffusion, you place the wafer in the full of the arsenide-rich gas, or you blast the wafer with the beam, arsenide ion beam. Okay, so this is the first process we done. Right now we got an end well. We can construct the PMOS transistor, and we also can construct the NMOS transistor here in this region. But in order for us to construct the NMOS transistor, NMOS and PMOS transistor, we need to put a gate. Okay, during transistor, you can see that we still have a gate. Okay, transistor gate. Okay, if you look something like this, the gate is somehow it's just like let's say a lock. Okay, what's a lock? Okay, because the gate is used to control how many current will flow through. Okay. I'm not sure whether it will still or not. During transistor, we got a gate. Gate is to control the current flow. Okay, so this process we are going to create the gate for the transistor, for the P substrate and the N well, for the PMOS and the NMOS. So in order for us to do this, we need to do the chemical vapor deposition to put a polysilicon. This layer is the gate layer. But funny thing is, we are not going to install one by one. We need to install first. We just remove part by part. It's just like what we did in the previous. Okay, we put it cover first, then we just focus on the area that we want. Same thing that happened to the polysilicon. If you want to put a gate, we also do it in the same way. Okay. So after that, we are going to remove the remaining area. Same thing that we did in the earlier. Okay. So the gate itself is used as a mask that establishes the source and the drain. Then the source and the drain automatically are exactly aligned precisely to the correct region. What is it about? Okay. After having the gate, we are going to install the drain and the source. Remember, the transistor, we are going to have the base, then the drain, and the source. Okay, now if we are having the gate, this gate can help us to align the position of the source and the drain, which is somewhere around here and here, or here and here. Okay, but don't forget we also need to install a base. So that's why I install another base here. Okay, so in order for us to use the source and the drain, remember for the PMOS, okay, PMOS is here, NPN. This one is the P plus, this one is the PNP. So this is a PMOS. Then this one is the NPN. N, P, N, N, P, N. Okay. So right now, we want to make it NPN and PNP. And this NPN and PNP actually is the reason for us to install the drain and the source. Okay, so with the help of the gate, we can know that where is the place that is suitable for us to install the drain and the source. So in order for us to install the drain and the source, we need to add these two regions. Because it is the NPN or PNP, we need to add the N plus region and the P plus region here. But before we proceed to the P plus, we install the N plus first. And somehow in the PNP, this one is the base. The base is using the N plus. So we install the N plus first. We install all the N plus together. Okay, so after we so right now, we are going to transfer the process from here to here. But how are we going to do this? Same thing happened. We just focus on this region. But right now, we are going to install the N plus diffusion because we want to deal with the P substrate first. Okay, so we have a self-aligned process because the gate is help us to do the self-alignment. Okay, so since we are going to have this thing to help us, this thing will be going to install to here, install to here, install to here. So say this thing is blocking here, so this thing will not be planted in here. And this region will be somewhere right in here, and right in here. So after this process, you can see that we are going to have this NPN and this thing, we still haven't done it, but we almost complete this part. Okay, this process we call it as a N diffusion, or maybe we call it as an N plus diffusion, because we are going to put the NPN. You might be wondering what's the NPN and PNP. Actually, it's the way that your current flow in the transistor only. Okay, if you still remember during the maybe basic electronic or microelectronic or basic electronic or non-electronic, you have seen these two words before. So after this, okay, we are going to remove the silicon. Then we are going to install the P plus. Just now is the N plus. Right now is the P plus. Okay, sorry, here. P plus. Because we are going to create the NMOS PMOS transistor here, NMOS transistor here. Just now we have done the first part. Right now we done the second part. We do the same thing. We do the injection here, here, and here. Okay, after the injection, right now, the NMOS and PMOS is actually almost complete. But in order for us to get it connected to each other, we need to put the contact. Or maybe you can think as the leg of the transistor. If you should remember, in the transistor we got a 3 leg. So right now we are going to create a contact for this region, this region. Then after the installation, we just put inside here, then connect to each other's. Okay. So eventually, in the end of the process, you will look something like this. Okay. Why are we going to have a contact? Because we want to connect these two transistors together. Okay. For example, this is a transistor, then you have another transistor here. Transistor here. Connect these two transistors together. So that's why we need to add the contact. The contact actually is a wire. Sorry, my bad. This is a wire, not the leg. Okay, we are trying to wire the device together. So in order for us to do the wire together, we need to use the tape field oxide. This one is a chemical net, actually it's not the important. Okay, for me, I think the important thing is the process. So after adding the contact, then we only put the metal. Metal actually is the leg, the transistor leg. Okay, so eventually the process you can see is something like this. This is the end product. The end product, you can see through transistor actually is trying to connect with each other. Something like this. Something like this. Okay, eventually this is the whole process. So one wafer. Inside the wafer, actually there are a lot of transistors like this. So this is the most simplest one. Some of you may have seen that actually the fabrication is something like this. Some of you just see this process only. Most basic one. Okay, you can see this at NPN. Okay, but somehow, if you want to have a more complicated circuit, okay, this is a two transistor connected together. Then somehow, maybe they are having the MOS circuit. Maybe they have a NAND gate circuit. Okay. NAND gate circuit, imagine you have a 4 transistor here, 1, 2, 3, 4. But you are going to put this 4 transistor into one small wafer, which is the tiny region inside, somewhere around maybe a square over here, this square. You need a 4 transistor. Okay, this is how you do it. Or maybe you want to put maybe 6 input NAND gate. Yeah, it's all this NAND gate. 1, 2, 3, 4, 5, 6. This is a 3 input NAND gate only, not even 6 input NAND gate. Only a 3 input NAND gate, you already need the about 6 transistors inside. So imagine one of the, let's say, microprocessor, for example, i3 processor. I don't know how many NAND gate inside there. Okay, you see this is a 4 input, 1, 2, 3, 4, 4 input transistor, 4 input NAND gate. Or maybe some of you may have interested in the NOR gate, 6 input NOR gate. Let's see what is it. Anna, any example here? Okay. Okay, this is 4 input. So this one, you can see this one is also 4 input only. Maximum can go to 4. But in the practical world, you can see a lot of transistors inside there. Okay, so far any question? Any question? If you have no question, then tell me no here. Okay, good. Everyone seems okay. Hopefully you can understand. Our time still okay. Ngam. So if no question, then I think I will end the class for today. Thank you very much for the attention. Yes, I will upload the slide and all the recording by either today or tomorrow. Okay. So thank you very much for your attention and have a good day. Enjoy your weekend. Bye everyone. And don't forget to submit all the proposal form. Today is the due date. Proposal form, don't forget. Enjoy your day, enjoy your weekend, and have a good day, everyone.